My name is Savannah. I'm responsible for all the marketing activities for SELTECH. It's nice to see so many of you joining our webinar today for CES SELTECH virtual event. It's time to our webinar. So, Julio, what is the plan for this afternoon?
Hi, Savannah. Hi, everyone. This afternoon, we will have our partners and friends from Knowles. The in-ear monitors used by professional musicians are almost exclusively based on multiple balanced armature drivers, as are many audiophile earphones. During this webinar, Bellavia of Knowles will describe the reasons why this is so, discuss design considerations, and share some practical examples. We will leave now Paris to join the windy city of Chicago, where Knowles is based. So take a nice cup of coffee, relax, not too much, and enjoy this webinar and stay safe. So, hi Andy, thanks for taking the time to share your knowledge with us. The platform is yours. Bye.
Thank you, Julio. It's a pleasure to be with everyone virtually today. I'm Andy Bellavia, Director of Market Development for Knowles. I've been working with Knowles for about 8 years now. And in that time, I've been involved in what we call the commercial side of hearing health tech, and that is everything which is not a regulated hearing aid. So in-ear monitors and professional musician earphones, radio communications devices, hearable devices, and so on, everything which is not a regulated hearing aid. And today we're going to talk about in-ear monitors, why in-ear monitors use multiple drivers, and how multiple drivers are implemented. I'm going to share my screen right now. Okay, there we are. Now, the first thing I would say about in-ear monitors is it is as much art as science. That is, even though you can measure a lot of things, ultimately, there's a lot of listening and adapting that goes into it. So, you can measure the frequency response, you can measure the distortion, but at the same time, there are a lot of things that are hard to measure. Listening with earphones is actually a bit artificial compared to listening to a live stage or loudspeakers. And so you think about, you put one earphone in your ear and it sounds like everything is in your head. You listen to another and you can hear and visualize the stage out in front of you. These are the things which are hard to measure, which makes designing a multi-driver earphone half art and half science. And we're actually going to talk about both. The first thing we have to consider is the ear's response. The ear itself is actually not flat. If you listen to a loudspeaker or loudspeakers with a flat response, your ear actually has resonances that mean what the eardrum is getting and what your brain is getting is not flat. You have the pinna, which is the external part of your ear. When we refer to an ear, that part that sticks out, that's the pinna. And you also have the ear canal, which is an irregularly shaped tube. So that creates resonances. Now, your brain actually EQs those out. So when you listen to a flat response loudspeaker, you perceive a flat response because your brain is compensating for the resonances which are there. And you'll notice there's one resonance peak above 10 kilohertz. That's actually going to come up a few times in the presentation, so I wanted to point it out. But when you put an earphone in your ear, those resonances go away. The pinna has no effect at all because you're injecting the sound directly into the ear canal, and the ear canal resonance goes away because what was an open tube is now closed. So when you design an in-ear monitor, you have to account for the resonances your brain is expecting but are no longer there. I'll give you an example. Etymotic ER4 series, they strive to have a perceived flat response. And so you see here, the response of the ER series actually mimics the ear response. Now it's done in two ways. We actually build the resonance in that 3 to 5 kilohertz range into the BA itself. And with acoustic tuning, you can shape it a little or whatnot because there's an interaction with all of the hardware of the earphone as well. So you can do a little acoustic tuning, but we build that resonance into the balanced armatures serving in the mid-range. Now the bass response, they actually introduced two series with two different bass responses. And of course, this is where you get into discussion about why you do things in in-ear monitors. They have the flat response and they have one with slightly boosted bass. I actually asked Carl Cartwright, who was formerly with the West Tone Music Division, about that as well, because they did something similar. And he explained that on stage, the wireless system that musicians use actually needs a little bass compensation. And so you get this sort of response. And also, when you're listening with an earphone, you get less of the visceral impact of the bass, which you can partially relieve by raising that low bass up a little bit. So you start with a neutral response, but then you can also start to adjust the earphone according to the sound signature you're looking for. A lot of debate on how much of that is appropriate, and yet people like different things, and so responses are tuned in different ways. But of course, the question is if you can achieve this sort of response with one driver, why would you use multiple drivers at all? And that's really what we're going to talk about in this presentation. The first thing is you can design earphone drivers for their particular slice of the spectrum, and they'll perform better there in the same way that they do with loudspeakers. In a loudspeaker, a woofer is designed differently than a tweeter. So you can extract maximum performance out of a driver designed for a portion of the spectrum as opposed to trying to cover the whole spectrum. Now, in the earphone world, there are some pretty good dynamic drivers, but ultimately, if you want to get the best, cleanest, and most controllable sound across the range, multiple drivers are the way to go. And that's actually why professional musicians use multiple driver in-ear monitors. You can really get good, clean sound across the entire spectrum. And since balanced armatures are small enough, one can do exactly that in an earphone that's comfortable. So here's a graphical representation of that. I show a balanced armature woofer and a balanced armature tweeter. In the woofer, that is designed, we design it specifically for the best possible performance in that small part of the spectrum. So we can get lower harmonic distortion at higher output levels out of a woofer than we can with an equivalent full range driver. And the same is true of the tweeter. Now you'll see in-ear monitors using multiple drivers as well. And the reason this is done, same as a loudspeaker, the distortion of a driver will go up as its output level is increased. And so if you operate two devices at a lower level, you'll get lower distortion in one device at a higher level. And for both audiophiles and especially professional musicians, it's extremely important. A professional musician wants to hear the cleanest possible sound. And so you'll see in-ear monitors actually running quad woofers. So you'll have 4 rather than 2 or 1. The other reason to use multiple drivers is that you can shape the sound more flexibly than you can with one because you're working with a crossover network just like in a loudspeaker. So I'll use an example here, the AKG N5005. It uses a dynamic subwoofer, a woofer dual BA, and then a dual mid-range tweeter combination BA. Now, there's many of you, I'm sure, have heard of the famous Sean Olive curve, where he's done a lot of blind testing to determine what people actually prefer in a headphone and earphone response, you know, apart from all the other information, the marketing information and so on. Just simply give people an earphone to test and let them describe their preferences through his testing system. And the orange curve is what you see. Well, this earphone was meant to replicate that curve, and you can see they hit it pretty well. And that's being done by adjusting the crossovers amongst the different drivers. It's harder to sculpt the sound signature this way with one driver. I also want to point out, you see at 10 kilohertz, you see that peak. This is the peak that I showed you in the ear response, but there's actually, in the couplers that are commonly used, that peak is a little bit overstated. We're going to get into that in more detail, but it shows up here, so I wanted to point that out. In fact, the coupler that's typically used isn't very accurate at all above 10 kilohertz. For that reason, Sean told me that in his evaluations, his blind studies, he actually doesn't look much about what's going over 10 kilohertz. He focuses on the bass and mid-range response and what people prefer there. You can also use the same driver combination and get different sound signatures. Now, there's a few people who are actually doing it with switches on the device itself. FIO, for example, has 3 switches on their FA9, and you can change the sound signature right in the earphone. Other companies will do different sound signatures in the same earphone, but offer them as separate products. This is, again, something you can do with multiple drivers that's hard to do with a single driver. There's another company, for example, who offered a 4-balanced armature unit for musicians with a dual tweeter, and that dual tweeter had a partially damped bass response. Well, they were getting some feedback from drummers. They wanted that low bass to be uplifted a little. They simply removed the dampers from the woofers and let the bass response raise up. And so they didn't have to change anything else about the earphone except for that. So you can shape the response in the same earphone by adjusting the crossover network, another advantage of using multiple drivers. In designing multiple driver earphones, it pays to take a step back and talk about the difference between dynamic speakers and balanced armatures. In the dynamic speaker, the coil is attached to the diaphragm, so the coil is moving with the diaphragm. In a small dynamic speaker, you have to be very careful about the mass of that moving element, the mass of the diaphragm and coil combination. So that means one is limited to the number of turns, the amount of copper that can be on the coil, and that means a little less versatility in the design of the device. If you put too much mass in the coil, then the dynamic speaker becomes less responsive. Now, the balanced armature coil is actually fixed. The only thing that's moving is the armature or reed and the diaphragm itself. So with the fixed coil, a lot more turns can be put on it, and that means there's a lot more range of DC resistance and a lot more range of impedance at a kilohertz that can be included. So the impedances of the various balanced armatures can all be adjusted so that they match each other in a multiple driver earphone. And in some designs, this is going a little bit far afield, like in hearing aids, for example, using Class D drivers, the balanced armature impedance is raised up quite high so that the Class D driver is very, very efficient. Now, you don't see that in wired earphones, of course, but as true wireless earphones move into the audiophile space to save power, you can start to see Class D drivers there as well. But the main point for purposes of this discussion is that you have a wide range of impedances available so that you can then make the drivers match each other very well. Now, the balanced armature driver is actually in a sealed box. And so in a certain respect, it makes designing with balanced armatures easier because you take a dynamic speaker, an open speaker, you then have to do all the calculations around putting that speaker in an enclosed, loudspeaker or earphone. So we'll even get some people who haven't worked with balanced armatures before asking for the Thiel small parameters to calculate out, the performance within the shell. You actually don't have to do that with a balanced armature. That's all done for you in effect, because the BA equivalent is to have a speaker in a closed box with a port. Now, you can back vent the balanced armature, and we do that because the way the speaker works in an enclosure is the air is stiffer at lower frequencies. And so if you have a small enclosure behind the speaker, the bass will roll off. The more space you allow behind the speaker, the more the low bass will come back up to its natural level. We'll pick the size of a balanced armature to be something in the middle. It's not quite as good as free air, but it's pretty good. And that's just a juggle between the size of the balanced armature and how much back volume you apply. If you want to let the bass go, then you can vent the backside into the earphone shell and the low bass will go a little bit higher. And I'll show that in a moment. Now, when you do a multiple driver setup, as with a loudspeaker, you have a crossover, but because of size constraints, the crossovers are a little bit different. You see an example of a crossover in a loudspeaker where you have inductors, capacitors, and resistors. An earphone is really too small to pull all that off, but there are a lot of other acoustic tools you can use. So you'll typically see capacitors or RC combinations as crossovers, and you tune the earphone by other acoustic means, which I will share. One of those is actually all the tubing from the balanced armature to your ear. In this case, you can actually see 3 different tubing sections. And as you adjust the tube diameter, you'll see the response change. So in that graph, you see the mid and high frequencies going higher and higher as the tube diameter is increased, which is a way of saying that narrow tubes cause some low pass filtering effect, which is also something you can use to your advantage. The same is true of tubing length. As you lengthen the tube, you'll get more low pass filter effect. And you can see that here. That's tube length increasing on the black line. So you see the frequency response really going lower and lower as the tube length is increased. Now, that's both something you have to account for and something you can take advantage of. I'll go back to the Theo FA9 again, because they actually do 3D printed tubes of different lengths. If you look, you can see the woofer tube actually kind of snakes around quite extensively to give a good low pass filter, an acoustic low pass filter to the woofer. I have to give some credit to Shure because they actually were, I'm pretty sure, the first one to do this in an earphone. In their 845 series or 845 device, what they did was they took a series of metal plates and stacked them. One plate would kind of snake or have a cutout, you know, that snaked around. Then the next plate had a hole that carried it to the third plate, which had more circular snaking around, and then the next plate. And so in a series of metal plates, they build up a long acoustic tube. And now with advanced 3D printing, it can be done that way as well. And getting that tubing right is actually very important. I'm using a tweeter as an example here. If you look at our tweeter WBFK and you put the raw tweeter in the measurement coupler, you see you've got that peak at about 5 kilohertz. It's really not that much to look at. But that same tweeter in a properly designed earphone, you'll get a lot of high frequency extension past the tweeter's peak. So getting the tubing right in an earphone really gives you a good response from the drivers. You can also use acoustic dampers. These are actually cloth meshes with different acoustic resistances. And here you see 3 different values of dampers and just how much they have an effect. So that the dampers effectively will reduce the peaks at higher frequencies. And as you dial in a higher and higher resistance damper, you see the high end being rolled off more and more. Now that can be done on woofers too. If you use a super high resistance damper on the output of a woofer, you'll get a lot of high frequency roll off. And so therefore you can actually knock off any of the higher frequency artifacts coming out of the woofer. But generally speaking, they're used on the output of the earphone or on the output of tweeters to shape the tweeter response. And not only the resistance value of the damper, but also its position within the earphone tube has an effect. And here again, we come to the back venting of the woofer. I show here 3 different values. With the red one, no vent at all, you see what the bass response is doing. Now, one other thing about having a no vent driver is you get the best isolation. That's an advantage of balanced armatures overall anyway, especially for in-ear monitors on stage, is that you want isolation from the loud stage environment. The purpose of wearing in-ear monitors is to protect a musician's hearing. So you want the best possible isolation, which you get from the balanced armatures in the metal can versus dynamic speakers that are open. But having said that, you can also open them up, and this is done more often in audiophile earphones where there's less of a hearing protection element than there in professional musician in-ear monitors. So if you look at the red line, you see the low bass is starting to roll off. That's the compromise between overall size of the housing and how much back volume is allowed. If you use a damped vent, and here what we do, you can do it two ways. You can either make that vent hole very small so it's resistive, or you can use a damper patch on top of it. Then you get increased bass with a certain shape, and then if you open the vent up altogether, the bass runs free. So there are many in-ear monitor companies who are shaping the bass response by damping those vents as opposed to letting them wide open and still getting a good bass response all the way down to the bottom. You can also vary the coiled DC resistance to impedance ratio, and this is a function of the flexibility we have in the non-moving coil design of a balanced armature. If you use fewer turns if you use thicker wire and wind a number of turns to get a certain impedance at a kilohertz, you'll have a different DC resistance than if you use thinner wire and wind enough turns to get that same impedance at a kilohertz. And you can see the effect here. If you wind the coil for a higher DC resistance while keeping the same impedance at a kilohertz, you'll get a lower bass response than if you wind a coil with a higher DC or lower DC resistance compared to the impedance of 1 kilohertz. And so in the design of an in-ear monitor, we can adjust that coil to help our customers get the bass response they want. Now, when you put it all together, the system actually becomes quite complex. And this is partly where science and art interact, because you have to get everything correct at the crossover points as well as the correct response out of the individual elements. And so you're playing with a combination of tubing lengths and diameters, the impedance and DCR of the drivers, how the woofers are vented, if they are, the crossover design itself, the dampers used, and especially getting the phase correct between the drivers. When I talk about art and science, not every company who designs in-ear monitors, including very good ones, has the equipment to measure the phase response in the crossovers. But if you don't get it right there, if the phase of the two drivers are not matching in a crossover, you'll get peaks or valleys at those points, which a person with a good ear can pick up in the listening. And so you can do this by listening and adjusting, or you can do the phase response by measuring as well. But all of these things interact with each other. And so when you wonder a little bit about why some multi-driver earphones cost so much, there's a tremendous amount of development time that goes into them, because all of these moving parts have to be accounted for. Change one and other things change as well. Now I want to close by talking about the coupler, because the coupler that up until now, well, including now, is still most commonly used is referred to as the IEC 711 coupler. It has an EN number that goes with it now. But that coupler is actually not good above 10 kilohertz, because in making a simulated ear canal, this coupler's peak, remember the little peak I showed in the beginning? The peak of the coupler is much taller and sharper than the ear response. And so I use here the example, the grass coupler. They won't even specify it above 10 kilohertz. And so you have a coupler being used to measure in-ear monitors that are only good for half of the spectrum. Of course, the natural question is why actually is that done? Well, it goes back to the coupler history, because the original reason for developing ear simulators was for hearing aids. And here I have to give Knowles credit, because the very first head and torso simulator with ear simulators was developed by Knowles. It's called KEMAR. Later, grasp bought KEMAR, and if you're interested, they have a nice little history of the KEMAR. But the first artificial head and torso with ears and with simulated ear canals and measurement microphones inside was invented by Knowles for hearing aids. And in hearing aids, even today, hearing aid frequency response does not go above 8 kilohertz. They're concentrating on the vocal spectrum and limiting the frequency response in exchange for higher battery life and smaller size. And so the coupler that's being used for earphones came out of couplers being used for hearing aids, because in-ear monitors were developed much later than hearing aids. And so we've all been kind of stuck with this coupler that doesn't cover the treble end of the spectrum. And that's another reason why in-ear monitor development has been art as well as science, because you could not actually measure above 10 kilohertz accurately with the couplers in use today. And I should just point out that when you're doing an in-ear monitor, you don't need the whole artificial head. The head is for over-ear headphones, for loudspeakers, and for devices with microphones, because the head and the torso shapes interact with those devices. And so you have to account for that by having an artificial head as a measurement system. But an in-ear monitor, since it plugs directly into the ear canal, you can plug the in-ear monitor directly into the coupler without needing the whole head. Now, another effect, aside from the fact that the frequency response can't be accurately measured above 10 kilohertz, is that it can also create artificial peaks in the harmonic distortion measurements. And the way that happens is, if you, when you are doing your sweep for measuring harmonic distortion, when one of the harmonics lands at that peak, it will be measured higher than it actually is. So here I have the peak is at approximately 12 kilohertz. So when we're measuring approximately 3 kilohertz, it's actually just slightly above. When you measure 3 kilohertz, the fourth harmonic is at 12, and so the fourth harmonic is amplified by that sharp resonance peak, and therefore the harmonic distortion measurement will come out too high at that spot. And the same thing would happen when you have the third harmonic at 12 kilohertz, so that would be at 4 kilohertz, and then at 6 kilohertz you'd have the second harmonic where that peak is. And so experienced designers have gotten used to seeing the THD profile looking good, except for these, peaks in a couple of different places, and knowing that that's a coupler resonance peak. But that's one other effect of having a coupler that doesn't measure the whole spectrum accurately. And so when you measure a frequency response, you always had to ask yourself, is that peak real, or is it just the coupler? Now, when you have an earphone with all the extra tubing lengths, that peak, which is roughly 12 kilohertz, and the coupler itself might move down. In this particular earphone, the peak shows up at about 9 kilohertz. And you have to ask yourself if that peak at 8 or 9 kilohertz is real or not. Because if that peak is real, you might get too much sibilance in the response. It may sound a little bit too sharp when you listen to the earphone. Now, in the past, what we would do is we would take a very small volume coupler and measure the treble response. Now, because of the small volume, you can't rely on this coupler for the mid-range and bass. Because it's much smaller than the ear canal, the bass will be amplified when measuring this coupler, so it's no good there. And in fact, even its response in the treble range isn't exactly accurate, because it isn't an accurate ear canal. It's not an accurate representation of the ear canal, but its resonant peak is higher than 20 kilohertz. So at least we could check the resonant peak with it. So we would measure an earphone with the 711 coupler across the whole range, and then above 4 or 5 kilohertz, we'd measure with the small volume 0.4 cc coupler and see if that peak is still there or not. In this case, you can see the peak is not there, and therefore we're pretty comfortable that we are not introducing a sharp peak into any earphone using this balanced armature device. Now, more recently, Grass, and I believe Head Acoustics has one as well, introduced a more accurate coupler. In this particular device goes out to 20 kilohertz and more, and you can see the peak is actually closer to the ear canal response. It doesn't have the sharp peak involved here. We've been using this coupler in our developments for a while. In fact, one of our engineers, Eric Viederholz, actually worked with Grass on helping to specify this coupler, doing measurements and so on when they were developing it. So we're very familiar with it, and we're now starting to use it across our own developments because it is more accurate in its response across the whole frequency spectrum. And I'll just close by showing this is one of our newer drivers, a two-way system called GM, measured with the high-res coupler. And you can see actually its response, you don't see any really sharp peaks out there. You see a response which is pretty clean of artificial artifacts with a coupler. So we're actually publishing our data sheets now with the new coupler, and we're starting to go back and redo all the older ones as well, so that customers can have a more accurate idea of what's going on with the driver and how it will sound in the earphone response. And we're starting to see our customers adopt this driver or this coupler as well. So now we can move to the question and answer period. Before we do, I just want to point out that if you want to know more, you can reach out to us at seltechinternational.com. You'll find easy links to SELTECH's global network. We also have a microsite on our website called knowlespremiumsound.com, where you'll find a lot of resources related to balanced armatures for in-ear monitors. And we have a lot of technical videos at vimeo.com/KnowlesCorp. You can also reach me personally at LinkedIn and Twitter, on LinkedIn and Twitter. So thank you all for attending, and now we can open it up for questions. Okay, so there's a question here. Will our ear canal in the end behave in the same way that a conventional 711 coupler? Wait a minute, I'm getting a note from SELTECH. I just want to make sure. Yeah, question section on the control panel. So yes, I found it. So will our ear canal in the end behave in the same way with a conventional 711 coupler? If not, except artificial head, is there a coupler really close to the human ear canal? Okay, so you actually anticipated the last part of my presentation. I hope that answered your question. If not, do let me know. All right, in multi-driver systems, how important is matching impedance between drivers? It's actually quite important, because if, for example, you have one impedance too high and one impedance too low, then the response will be quite mismatched, because more of the drive current will feed the low impedance device. So too low, you'll get it one way or the other like this. And so it actually is important. I mean, some of that can be taken up in the crossover and with some resistance. But generally speaking, if you're really trying to fine tune it, you want to use impedances which are matched to each other. So yeah, there's some playing you can do after the fact, but you can't be too far off in the impedance matching. And as I mentioned, also part of impedance matching is also making sure you get the phase right between the drivers as well. Do we provide software doc or model for tubing design? The answer to that is yes. And actually, the tubing can be modeled in PSpice, where you kind of work with electrical equivalents to the acoustics. And we have a variety of assistants we supply there. And that's something you can discuss with our engineers quite readily. We've got SPICE models for the drivers, and we can supply SPICE models for the tubing elements as well, and help in that way. So there are lots of different ways we can help with modeling, and we'd be glad to do it. Just reach out to us. How do you advise measuring the driver's distortion to assess their sound properties, second and third order harmonics mostly? Well, if you have the equipment, you can measure the THD directly. Some companies will simply do it by using a person with a good ear. Now, if you're starting out with balanced armatures that have low THD, that typically is not going to be a problem in the final design. If you get phase mismatches, you're going to have holes or peaks in the response. But for the most part, the THD of the drivers is going to affect the THD of the complete earphone. It's part of having that kind of driver system put together for you. And if you want to dive into it in more detail, I can definitely hook you up with one of our acoustic engineers. What are the key indicators you are looking for during development frequency response THD? That's a really good question. And what we'll typically do if we design a new balanced armature, we'll start with a reference, if you will. And actually, it's those references which you see at KnowlesPremiumSound.com. So we made, for example, a new woofer called RDI. Its whole focus was on 1 kilohertz and below. And so what we did was we designed that driver for lowest possible THD at 1 kilohertz and below. In other words, lowest possible THD for a given output level. So we had one called Hot VTEC. It had a really good THD versus output profile. Now we made an improved version. So that was the design target. If it's a tweeter, we're going to design for high frequency extension with low distortion. How far can we push the high frequency? Can we get the high frequency level out? Can we get the high frequency level extended? So it is really, it's output at the frequency range of interest versus distortion. And so then once we get the reference design, the models will start to proliferate depending on the needs of the customers, like coil impedances, for example, like venting options, for example. Those are the things that we can then change according to different needs. And so if you look at a mature driver like our ED, which can be used as a full range driver, it's sometimes used as a woofer mid-range, and sometimes it's used as a pure mid-range, and it's also popular in hearing aids. We have hundreds of different models at this point. And so if you're looking for an ED with, you work with one and you need a little bit lower coil impedance, chances are we already have it. And so the models start to proliferate after that. But we always start with that combination of frequency response and THD in the band of interest. Are there plans in implementing new/different technologies, for example, electrostatic treble drivers or magnetostatic ones? So at the moment, we don't have on a near horizon an alternative technology. We are constantly working on improvements to the balanced armature technologies. And in the future, we may end up with alternative technologies as well. We have all the expertise in-house for that. For example, we've been making electret microphones for a long, long time. And so we could actually make an electrostatic tweeter on the basis of that. But we're going to have some interesting things coming with balanced armature tweeters for improved high frequency response. Stay tuned for that. And the reason why that is our next development is because a balanced armature is very easy to implement. Balanced armature tweeter is very small, doesn't require a high drive voltage or external transformer, which keeps the size way down. But I won't rule out that in the future we do some of the others, and we're very familiar with and have the capability of doing those other designs as well, should we choose to do so. And when you think about also true wireless devices, you're even more limited with what you can do there. But of course, those are different needs than for in-ear monitors, where it's quite possible to implement, for example, an electrostatic tweeter. Can Knowles provide single damper pads for woofer vents tuning? Yes. I mean, more typically what we're doing is we're providing the damper pads on the woofers for our customers. So they're pre-assembled with the damper patches and then tested accordingly. But we can discuss supplying those separately if it's a Knowles balanced armature on the other end of it. All right, I think there we go. Can the BA handle some amount of DC in a DC bias system? I actually don't know the answer to that question. I'm going to have to get that one answered by one of our engineers. I don't want to speculate. I can't answer that question. But let me ask, Savannah, is there a way to identify the person who asked that question? Or whoever asked that question can reach out to me and I'll get you the answer. In fact, the SELTECH's acoustic engineer based in Paris can answer that question directly as well. So I'd be glad to help get that answer for you. Savannah just sent me a note. Let's see what she said. Okay, she answered yes. And so, yes, we will take care of that question for you. Sorry I couldn't answer directly right now. Doug Levy, who left, said Carl Cartwright was Westone, not Etymotic. Yeah, Carl Cartwright was with Westone's music division, never with Etymotic. I was quoting Carl. I was showing the Etymotic response, but quoting a conversation I had with Carl. All right, next question is, do you find that balanced armature in-ear monitors are better, worse, or neither for avoiding the occlusion effect in ear seals? So that's a really good question, and it actually comes up more in consumer earphones than it does in in-ear monitors, because in in-ear monitors, the goal is actually to have a tight seal so that you get the hearing protection that you desire. But in a consumer earphone, especially when people are on the go, they want less occlusion effect. And so then you get into the question, well, how do I minimize the occlusion? Now, to minimize the occlusion, you really need to have a bigger driver. You need to move more air, because to reduce the occlusion, you're putting a leak in the front side, and that leak will cause low bass roll off. So you can drive against that. And if you're trying to create kind of a semi-open design to reduce the occlusion, it's usually better to use a dynamic driver there, because you can drive against a bigger leak that way. Now, what you see for earphones for audiophiles that are trying to reduce the occlusion, it's going to a hybrid design. So you use the dynamic woofer and you drive against that leak to get the most bass possible, but then you have the balanced armatures giving you that clarity at higher frequencies. So that's another option which is becoming more and more popular. Now I have a question here. How is the Sean Olive curve influencing the new driver designs? So it's an interesting question, and that is when we do driver designs, we'll usually start with a reference. So when we make a new driver, we'll start out with one reference sound. And because balanced armatures, although they're increasingly going into consumer earphones, they're still very much used by musicians and audiophiles, will tend actually to go towards that Sean Olive shape of the bass and the mid-range in our references. But then what happens is, as a particular balanced armature design becomes deployed in the field, people want different things. And so design variations will proliferate. We'll do different coils and the like for whatever people want. And including a leaky seal like we talked about before. You don't want to get carried away, but you can introduce some leak in a balanced armature earphone as well. And we would create a woofer, and if assistance is necessary, help the customer design the entire earphone to maximize the bass to drive against that leak. Same thing with other shapes. We've seen in different regions around the world, people prefer a little bit different things. Some people like the earphones a little bit brighter, which puts the vocalist out front and center. And so we will be responsive to what people want, and therefore we'll end up with a lot of different designs. If you look at a mature product like our ED series, which can be used as a full range, it can be used as a woofer mid-range, and it can be used as a pure mid-range, and it's also used in hearing health, you'll see literally hundreds of different design variations at this point, which is also good, because if a particular coil impedance is needed or so on, there's a very good chance we have it already. Was Dr. Meade Killian the person who started the original Etymotic designs at Knowles? That's a great question, because Meade Killian was an early Knowles employee along with Hugh Knowles himself, and there were a couple of other people whose names I don't remember right now, who formed the core of the original Knowles. But it was after Meade left Knowles and formed Etymotic that he started working on the in-ear monitors for Etymotic. He's a fascinating person, and a lot of kudos to him because he was very early on an advocate for hearing protection, both for musicians and also for ordinary people. So long time ago, for example, he developed, developed flat response hearing protectors, passive hearing protectors with flat response, for example, for concert goers and the like. What is that website about audio acoustics resource? It's knowlespremiumsound.com. That's our section of the website specifically for in-ear monitors and music earphones. And I have, does Knowles have any balance armature for hearing aid space that goes beyond 10 kilohertz? Well, that's actually more the choice of the hearing aid manufacturers. So we've got balance armatures that go all past 20 kilohertz. And I think what you're going to see going forward as the hearing aid processors continue to get better and better, consume lower and lower power with more and more processing capability, that hearing aids are going to start extending their frequency response as well. And so just as we have balance armatures for music earphones, we also could supply balance armatures above 10 kilohertz for the hearing aid space. Not an issue at all. And in fact, that's becoming more and more important because wearing hearing aids for live music, for example, or listening to, say a smart speaker streaming high-res audio, well, hearing aid wearers are increasingly wanting full spectrum response. And many hearing aids can stream either using the made for iPhone system or Bluetooth, and it's the same thing. If you take a current hearing aid and stream with Bluetooth, you're only going to get the 8 kilohertz when users are wishing for more. So I think you're going to see that coming. What is the IP rating of BAs? So it actually varies a lot by BA, and we also have special techniques for improving the IP rating of some of our BA models. If anybody is interested in using balance armatures in an IP rated earphone, we should talk because the moisture mitigation efforts we would use will vary by driver model. And thank you, Pierce, for that comment of appreciation. I appreciate it myself. And with regard to ANC earbuds, can the occlusion prevention leak be designed so it doesn't leak in too much noise for cancellation? Yeah, that's really a balancing act. And you have multiple factors in the balancing act there. The bigger the leak, the more you must drive against it. The more you must drive against it, the more power you consume. And especially if you're using ANC, then you've got to drive a lot of speaker power, both to mitigate the external noise and against that leak. So, and different people choose a different point on that leak. I'll use the Apple AirPods Pro. The AirPods Pro, I'm an Android phone user, but I bought an AirPods Pro and borrowed an iPhone to try it out. And they are really comfortable. And they use a fairly big leak, and they have a powerful speaker to drive against that leak. So it can be done, but it does cost you in power to do that. And so other people choose to use a smaller leak that they don't have to drive against quite so much and get a little bit more power efficiency. But then, you're juggling just exactly how much occlusion effect are you mitigating. And still newer systems are starting to actually go with active occlusion reduction, because occlusion is just simply the sound inside your ear canal. You can actually reduce the occlusion effect in the same way you do ANC for external noises. So there's lots of design choices to be made and different ways to make that happen. Is it possible to get a recording of this webinar? And thank you also for the comment, Shay. I'm glad you liked it. And I'm looking, Savannah, I believe we're going to record this webinar and make it available for playback. Is that true? I'll see if she answers me. And Renee, thank you. I appreciate your comment as well. I'm glad you enjoyed the webinar. And yes, Savannah said that the webinar will be shared as a recording afterward. And yes, also, Renee, thinking about electrostatic drivers, we're looking at all different things. And at the moment, I can tell you that we don't have on the near horizon alternative technologies. I mean, some of them, well, we know when we have experience with all those different things. But for the moment, we've decided not to. I can tell you that we're working on improving our balanced armature tweeter designs so we get more high frequency and more high frequency extension, even beyond what we have now, which will offer certain advantages because a BA tweeter is very small and you don't need a high drive voltage or an external transformer, which takes up a lot of size either. So, you know, we're working on different ways of extending the high frequency response, but we also have familiarity and capability with electrostatic tweeters and also the electric style tweeters. And I have a question here. BA stands for what again? Balanced armature. And that comes from the fact that the moving part that connects to the diaphragm, the armature, is actually balanced between two magnets, and that armature is magnetized by the fixed coil. So when audio is fed through the coil, then the magnetized armature will move within the magnetic field of the fixed magnets. So the armature is balanced within those fixed magnets, hence a balanced armature. I want to go through all the questions and make sure I got all of them. I believe I did. If I missed a question, please reiterate it, but it looks like I have all of them. All right. Well, I thank you all for attending. I hope you all found it useful. It's been a pleasure to meet in this way. Another time, maybe we'll do this face-to-face in a meeting room somewhere for CES or for another event. Take care, everyone, and have a good day.